Hello everyone, and welcome back to another statistics video. In this video, we are going to focus on discrete random variables. We're going to talk about what they are and how we read their tables and how do we analyze the functions. So let's get started. A random variable is a numerical measure of the outcome from a probability experiment. So its value is determined by chance. Random variables are denoted using letters such as X. And we're going to really focus on, in this section, discrete random variables. So discrete are things that we can count. We can also talk about continuous random variables, which we're going to see in another video, and we're going to talk about the normal distribution that's tied to those. So with discrete random variables, we're either going to have a finite or a countable number of values. So think about when we talked about discrete versus continuous data. Discrete was things that we could typically count. So the number of siblings we have, the number of cars that's in our driveway. So we're collecting data like that, maybe the number of siblings we have, and we're doing a survey and we're basing our probabilities on that survey. Maybe, for instance, we could let X equal the number of siblings. So maybe we've interviewed people and we've discovered that there's 0, 1, 2, or 3 siblings in our sample. So we could create a table associated with that. And we could find the probabilities associated to each. Maybe we asked a total of 20 people how many siblings they had. Maybe we had 5 of those 20 have 0 siblings. Maybe we had 7 of those 20 have 1 sibling. Maybe we had 6 out of 20 have 2 siblings, and 3 out of the 20 have 3 siblings. So then that would create that probability distribution, but it's all tied back to the idea of whatever we're looking at is some kind of discrete data and then finding the probabilities associated with our sample. When we talk about a continuous random variable, and we're going to see this when we talked about the normal distribution, we're now thinking about things on some kind of continuum scale. The probability distribution of a discrete random variable provides the possible values of a random variable and their corresponding probabilities. And usually you're going to see this in some kind of table or chart. Sometimes you'll see it in a graph. So what are the rules associated with a discrete probability distribution? So when we talk about the probabilities, the first rule is that if I add all the probabilities up, it's got to add to 1. So this notation means sum of the probabilities. That in written out means all the probabilities must add to 1. And the second rule is that each probability has to be some number between 0 and 1. Okay, we cannot have a probability bigger than 1. We cannot have a probability less than 0. If we want to find the mean of a discrete random variable, we're going to have this table of values. So x's and probabilities. So the mean we can find by taking each x value, multiplying it by its probability, and then we're going to add all those numbers together. So the mean ends up being the value that we're approaching in the long run if we were to replicate the experiment over and over again and look at those probabilities. Another word you'll see associated, or another phrase you'll see associated with that mean is expected value. So expected value is really the same thing as finding the mean of a discrete random variable distribution, and it's found using the same formula. If we want to find the standard deviation of a discrete random variable, we're going to take each x value, we're going to subtract its mean, and then we're going to square that. Then we're going to multiply that by the probability associated in that row, if we're thinking about this in terms of a chart. We're going to add all of those numbers up, and then we are going to take the square root. And that is our computational formula for finding that probability. So let's look at a few examples. This is where you may want to pause the video, read the example, and then come back and check your answer. First thing we're asking is this a valid probability distribution? So there's two things we have to check. First one, do all the probabilities live between 0 and 1? So in this case, our probabilities are all numbers between 0 and 1. So the first requirement is good. And then the other requirement, and it doesn't matter what order you check them in, is that the sum of the probabilities have to equal 1. So if I were to add these numbers up, what do I get? So my sum of the probabilities, I'm going to do that off screen. So 0.22 plus 0.16 plus 0.21 plus 0.16. I got 0.75. And that is not equal to 1. So we would say, no, this is not a valid probability distribution because that requirement of the probabilities adding to 1 does not work for this. Let's look at the second example. So once again, all my probabilities are okay. They live between 0 and 1, so that one requirement is met. So now let's add all the probabilities up. If I were to add all of these probabilities, do I get 1? Well, when I added them, and I'm adding them in the calculator off screen, I got 0.984. So again, no, this is not a valid probability distribution because it's not adding to 1. Let's look at that next one. We're talking about the Baseball World Series. There is a 0.1919 probability that a Baseball World Series contest will last 4 games. So 4 games. X is the number of games. And then this is the probability associated with that. There's a 0.2121 probability that will last 5 games. A 0.2222 probability it will last 6 games. And a 0.3737 probability it will last 7 games. So we got 4, 5, 6, and 7 games, and then probabilities associated with them. A is asking us, do we have a valid probability distribution? So we need to check the requirements. All of the probabilities live between 0 and 1, so that requirement is met. Now let's find the sum of the probabilities. So when I add these up, I ended up with 0.9999. And that's really close to 1. So I'm going to say, yes, this is a valid probability distribution. And the reason that it's close to 1 and not exactly 1 is because there's probably some rounding error associated with those probabilities. Notice everything's rounded to 4 decimal places. We don't have the fractions that are the exact values. If we had the fractions with the exact values and we added them, we would end up with exactly 1 there. So rounding can cause an issue with it going exactly to 1. So then the question becomes, how close do you have to be? You got to be super, super close. So if you get 0.9999, that's close enough. That last example where we got 0.984, that was not close enough. That's pretty far away from 1. If we would have ended up with something slightly over 1, like 0.0001, we would say that that's okay for a sum. So now that we have that, let's look at part B. Assuming that the given information describes probability distribution, they want us to find the mean and the standard deviation. So we're going to set up a table here. So I've got x and p of x, and I'm just going to add on a column. So my mean formula is the sum of x times p of x. So I'm going to take 4 and multiply it by 0.1919. And that's going to give me 0.7676. 5 times 0.2121, 1.0605. 6 times 0.2222 is 1.3332. And 7 times 0.3737 is 2.6159. So the mean is going to be the sum of all those values. I'm going to add all those up. So 0.7676 plus 1.0605 plus 1.3332 plus 2.6159. And I'm going to get 5.7772. So my mean is 5.7772. So now let's find the standard deviation. Standard deviation is the square root of the sum of x minus the mean squared times p of x. So I need to take x minus the mean, and our mean is 5.7772. And then I'm going to take that value and square it. And then I'm going to multiply that by p of x. So I'm going to start with 4. So I'm going to take 4 minus 5.7772. And I got a negative 1.7772, but I'm going to square that. And then I'm going to multiply that times the probability. So times 0.1919. And I'm around to the 4 decimal places, 6061. Then we're going to do the same thing with 5. So 5 minus 5.7772. So that's going to be this number squared. So I'm doing this in the calculator. Make sure you use parentheses around it, just like I've written. So minus 0.7772 squared. And we're going to multiply that by the probability. So times 0.2121, 0.1281. And the same thing with 6. 6 minus 0.57772. 0.2228. So I'm going to square that in the calculator and multiply it times 0.12 by its probability, which is 0.2222. 0.0110. And then 7. So 7 minus 5.7772 is 1.2228. So I'm going to square that, then multiply it by its probability. So squared times its probability, 0.3737. So that's going to give me 0.5588. Now I'm going to add this column. So when I add this column, I get 1.304. And then our standard deviation is going to be the square root of that sum. And when I plugged that in my calculator, I got 0.1419 for my standard deviation.